The next problem is going to take our ideas about optimization and kind of give it a little twist. We're not particularly given just one thing to look at. We're actually given all the closed plane curves in a plane. So of all the closed curves in a plane that you could do, and we're kind of assuming regular closed curves in a plane like squares, triangles, pentagons, hexagons, nonagons, etc., octagons, with a perimeter of 10, which one is the one with the greatest area? So this is actually a question that was first posed by Archimedes. Archimedes was a Greek mathematician, philosopher, etc., who first thought about these ideas and was very close to the concepts of calculus long ago. And then he was killed by the Romans, and everything was lost with him. And they were not discovered again until Newton and Leibniz discovered them in the late 1600s. All right, so let's begin with the closed curves. So the smartest ones to choose would be a triangle, right? So triangle, a square, and you could do a hexagon, a nonagon. I mean, you're welcome to, but I think you'll see what's going to happen. So I'm just going to do a circle, and then we'll discover what's going on with that. And I'm going to give all of them a similar value. So x is going to be used for the sides for all of them. Okay, wonderful. So there's my diagrams and there's my variables. And of course, I could do that for any of them. So I mean, I could draw a hexagon and use x as the sides or something like that. But you'll see the pattern will develop with just these three basic ones. And then you'll understand at the end how octagons and hexagons and such would fit. Okay, so number two, this is going to be a little weird because we actually have multiple objective functions because we're trying to find the one with the greatest area. See that? So the objective functions, there's more than one because the area will change depending on the problem or which figure we're looking at. So we want to think about the triangle figure. So the area of a triangle is a function of x and the height. All right, we're going to have to think about that. But it's 1/2 x times height. The height being what goes vertically down it, right? And just for the record, when you look at a triangle, the triangles with the largest area are equilateral. That's why I didn't even bother with, a weird isosceles or something with an acute angle or something, or sorry, a very obtuse angle. All right, so I'm going to leave myself some space there because I've got some work to do there. And then I'm going to move from there onto the square, right? So the square has, I'll leave myself some space. So the square has area, and it's actually already just a function of x because it's x squared. Easy, right? So I don't even need a constraint on that one. And then a circle, the area function is also x, a function of x, because it's pi x squared. See, by naming x my radius, I made things easy. So the hardest one is actually the triangle. The triangle is kind of a pain. We need to find a value for h. So let's think here. If I look at that triangle, let me give myself a little bit of space over here, and I kind of take it, and I take one piece of that triangle, say like this piece, and I say that this is the height right here, then this side over here is x, and this over here is x divided by 2, right? Because it's half of x. It's from here over to here, right? So I'm looking at basically this portion of the triangle. Okay, well, I have a relationship that I know of that relates those sides. So that's a constraint that I have. So the constraint that I have is that since it's this triangle, I know x over 2 squared plus h squared has to be equal to x squared. Pythagorean theorem. Now I need to solve this for h. So that would be h squared equals x squared, take away x squared over 4, because that's x squared over 4. That would be 4x squared over 4, because you'd make this 4 over 4. And that would make h squared equal to 3x squared over 4. right? Because 4 over 4 take away 1 over 4, which means h is the square root of 3x squared over 4, which is the square root of 3 times x over 2. Or let me put this, square root of 3 over 2x. That's fine. We'll just leave it like that. All right, so all of that is my constraint. So that's actually step 3, right? So there's step 3. There's a constraint. Right? Okay, now I'm going to use that constraint, and I don't need it over here. So the only one that needs a step 4 is right here, because I'm going to change my area function into area of x, and it's going to be 1/2 times x times square root of 3 over 2 times x. That's my h, which would be the square root of 3 over 4, because square root of 3 over 4, because 2 times 2 is 4, x squared. That's the area function. So here's one area function, here's an area function, and so on. So the only one that needed a step 4 is right here. Step 4. Right? Using the constraint to make it one variable. The other two actually didn't need one. If you did hexagons and nonagons, they would probably also, I'm thinking about geometry, they would also need some extra work, which is one of the reasons I avoided them. Okay, so now let's think. I know one other piece of information. So I have another constraint. Not so much a constraint as an idea, which is that the perimeter on these is 10. See that? So if the perimeter is 10, so this is constraint, if you will, constraint number 1 up here, and I actually have a constraint number 2. And constraint number 2 is that the perimeter is equal to 10, right? I only have 10 whatever, 10 inches, 10 centimeters, 10 whatever to make this. Let me pretend it was meters. Let me pretend meters. I'm going to add meters into this. All right, so if I say that's meters, then I have 10 meters. Okay, well, the perimeter on a triangle, let's look back up. The perimeter on this triangle is x plus x plus x. Right? And you're thinking, why am I not using this one over here? Well, I only need this one to get an h out of it. Right? That's the reason. That's what I was doing. So I don't need that for the perimeter part. The perimeter is 3x. So for the triangle, the perimeter is 3x. So 3x equals 10, so x equals 10 over 3. For the square, the perimeter is x plus x plus x plus x, right? So 4x. So 4x equals 10, which would mean x equals 10 over 4, which is 5 over 2, or 2.5 if you want to think of it that way. The circle, the perimeter is called something else. It's called the circumference, right? So for a circle, the perimeter is 2 pi r, in our case 2 pi x, which means x would be 10 over 2 pi, which is 5 over pi. So now that I have these values, I can plug them in. So I'm not really going to do steps 5, 6, and 7. I don't really need calculus to do this. I'm kind of just using my formulas, and then I'm substituting in these values. So I'm actually going to figure out which has the max area. So that's step 1, that's step 2. Right? This is actually step 3 some more. Right? So now which has the max area? Okay, well, let's look at the triangle. The triangle has an area that is, it's area of 10/3. Sorry, that's what I'm doing. 10/3 going in. So I'm going to take 10/3, I'm going to plug it in. So that would be, the square root of 3 over 4 times 10/3 squared. Okay, well, we grab a calculator, right? You make a calculator do this. And what you're going to find if you use a calculator is that it's 4.811 centimeters squared. Okay, now what about the square? The area function for the square is going to be the area of 2.5, or 5 halves, either way, right? Which would be 5 halves squared. Simple as that. which is 25 over 4, which is 6.25. So I'll just say that. So it's 6.25. Oh, I made these meters. Sorry, not centimeters. Meters squared. Forgot. And the circle, the area function is pi x squared. So I'm going to take the circle of 5 over pi, which would be pi times 5 over pi squared. And that comes out to, and again, I just used a calculator to do this, it's 7.958 meters squared. So what do we notice? We notice that as the number of sides increases, the area increases. And the most sides you can have, if you will, and this is what Archimedes was discovering with the method of exhaustion, is a circle. So if you take a circle and you let polygons, like put a triangle in it, put a square in it, put a hexagon, right? Then a septagon, then an octagon, then a nonagon, and a decagon, and so on. And you let it get closer and closer and closer, it's approaching a circle. It's the beginnings of an idea of limit, and he didn't realize it. Right? It was called the method of exhaustion. So what we see is that as the number of sides increases, so if you take your, as the limit as n goes to infinity of an n-gon, so let me put it this way, area of an n-gon is what that's called. So n being the number of sides. So a triangle is a 3 polygon, a square is a 4 polygon, right? A pentagon is a 5-sided, right? A hexagon is 6-sided, septagon is 7-sided, octagon is 8-sided, and so on. So if you let the number of sides go to infinity, you're approaching the area of a circle. Provided that, of course, you're keeping the perimeters the same, right? N-gon with same perimeter, let me put it that way, right? Because, of course, you can make a triangle bigger than a circle if you just give yourself a lot more wire to make the triangle than you do the circle, right? That would work. So if you take an n-gon and you let the number of sides on that n go to infinity, then you're going to be approaching a circle. In other words, the circle has the maximum area. Is the planar figure with the maximum area. And Archimedes was the one that was first figuring this out, and then it was lost to history.